point charge that we calculated. Then we calculated the electric field due to multiple charges, and we used the superposition principle. And now then we came to calculate the electric field due to a dipole. So we were calculating that. So let us find out that, and we did one part. So we understood that there are two positions of a dipole. One is called the axial position, right? This line is called the axial line, and this line is the equatorial line. So we already calculated the electric field due to axial on the axial point. That we calculated, and that came out to be 2 kp by r cube, where this p vector is the dipole moment. So this gives us the strength of the dipole. So we see that for the axial point, right, electric field is in the same direction as the dipole. So in here we saw that the electric field is in this direction, right direction, right? Now we will calculate the electric field due to the dipole on an equatorial point. So let us calculate that. How much would be that? We have this time I will not use this shape. So previously it took a lot of time to just find. Will not do that mistake again. So electric field at the equatorial point of a dipole. We have a dipole. This is minus q, and this is plus q, right? This is the center point, and let's say that this is so this was A, this was A, right? And this was the direction of the dipole moment. So we'll come to this point later. But this is this perpendicular is the equatorial line. This perpendicular is the equatorial line. And we are calculating the electric field at this point, right? So, and let us assume that this distance is r from the center. So this is r, this is a, okay? And let's say this is point B. And let's say this is A, and let's write it with different colors. So this is point C, this is point A, this is point B, right? And this is the separation, this is the separation, right? Let's say that this angle is theta, so this angle would be theta, because these are the same distances, right? This is R, this is A. So this would be how much distance? AP would be how much? Using the Pythagoras theorem, right? We have this triangle, this is R, this is A. So you want to find out this AP, right? Let's say this is center is M. So AP would be root of A square plus R square. Let us write it in a proper manner. So R square plus A square. So this is root R square plus A square. Similarly, this is root R square plus A square. Right? Is that clear, guys?
Yes, sir.
And how many contributions would be there at this point if you want to calculate electric field at P point? So how many contribution would be there? How many
Sir,
contribution?
on P point,
Yeah, on P point, how many contributions would be there?
sir, 3.
So what are the three charges that you can see?
So minus Q and plus Q.
And then what is the other one that you are seeing?
107. Okay.
Only two, right? So
Yes, sir.
electric field due to A and electric field due to B. Only two contributions, right? Is that clear, guys?
Yes, sir.
Okay. So now we are calculating the electric field due to A. So that would be attractive or repulsive. What would be that? Yes. Due to minus Q, that would be attractive or repulsive. Where would be the direction? Towards A or away from A? Due to minus Q.
Mm. So what's the charge on P? It's E.
We always assume that test charge is positive, right?
Okay, sir. So it's attractive.
Attractive, right? So it will be towards A, right? Correct?
Yes, sir.
And due to
Yes, sir.
B, towards B or away from B?
Away from B. Okay.
Away from B, so in here. This is EB, right? Is that clear, guys? Is this clear?
Yes, sir.
So let me write it in here, right? So this is E. So if I draw a horizontal line in here, right? So this is my x-axis, this is my y-axis. Okay. And this is my EB, right? And this is theta. So what would be this angle? This is theta, so what would be this angle?
Yes, sir. Can you repeat the question?
This is diagram is like this. This is theta, so what would be this angle?
So theta.
Right, alternate interior angle. This is
Interior line, yes,
theta,
sir.
so this is theta. And this is theta, so what would be this angle? This is theta, so what would be this angle?
So that will also be theta because the angle is the same,
Because,
right, as B.
yeah, because the corresponding angle, right?
Yes, sir.
This one is corresponding angle. This one and this one, right? This one, these are two parallel lines. This one is the transversal. This is theta, so this would be theta. Understood this point, everyone? Is that clear? Is
Yes,
that
sir.
good? So now you guys can tell me that EA vector, right? So let me write it in here so that it would be easy for you guys to understand. So we have this X and Y. This is EA with my angle theta in here, right? So EA will have two components, one in this direction, other one in this direction. Clear?
Yes, sir.
And I have told you guys that this part is very, very, very important, resolution of vectors. So what would be this part? Magnitude is EA. What would be this part? The angle one is always the cos theta part. And whatever is away from angle, that is the sine theta part. That we have understood, right? So if we have this, let's say L, and this is theta, so this is L cos theta, this is L sine theta. That we have understood in resolution of vectors, right?
Yes.
So similarly, using that part in here. So if I write EA vector would be how much? That would be EA cos
Cos
theta.
theta.
And what is the direction? What is the direction in here?
So theta.
Direction. You have X and Y axis. What is this direction?
Negative x and
Yeah, negative X, which is I hat, is the direction. I, J, K are the direction, right? And then you have EA sine theta. And what is the direction?
negative j.
Negative J. Right. So this is, we have got EA. Right. We have got EA. So let us keep that. And what would be EB vector? So EB vector is this one. What is EB? Yeah. This is EB, and this is theta. Right. So what is this component? What is this component? This is EB, this is theta. So what is this component?
EB cos theta.
EB cos theta. Absolutely correct. So why are you hesitating? What is this part? Yes.
Yeah, yes, sir.
What is this part? Vertical part. Vertical form.
Oh, sir, that's sine theta. EA.
Well,
EB sine theta.
good. So now we have got the vertical component, horizontal component. Then we can write this as again EB cos theta minus I and EB sine theta j hat. Is this part clear, everyone? Arslan and me, is this clear?
Yes, sir.
Okay. So now we have to add okay, before we do that, let us find out what would be magnitude of EA and what would be magnitude of EB, right? So for point particle, let me write it in here so that it is good. So for point particle, this is the point particle, this is the distance, right? This is a Q charge, this distance is R. So, and we are calculating the electric field at this point. So what is the electric field magnitude? How much is that? That is KQ by R square. That is the electric field of a point charge, right?
Yes, sir.
So similarly, if I calculate the magnitude of this minus Q charge at P point, I'm calculating EA magnitude, right? So for EA magnitude, this is point P, this is point A, this distance is root of R square plus A square. This is minus Q, so we take only the magnitude part. So EA would be how much? How much would be EA? KQ by separation square, right? Is that correct?
Yes, sir.
So this is kq by r square plus a square. This is the magnitude EA. Similarly, if we calculate EB, so then again that is same separation, same charge. So similarly, EB would be how much? EB would also be KQ by root of R square plus A square whole square. So that is again this one. So from here and here we can write that EA equal to EB, right? This
Yes.
is part. Okay, so now we can solve this part. So we know that electric field at P, this is EA plus EB, right? EA we have calculated. EA is minus EA cos theta, right? So EA is minus EA cos theta I hat minus EA sin theta J hat. Similarly, what is EB? EB is minus EB cos theta I hat and plus of EB sin theta J hat. So which part will cancel out? Which part will cancel out?
Sir,
Yes.
EA,
Because all these magnitudes are equal, right?
yes.
A equal to EB. So we can write this one as minus EA cos theta I hat
Sir, minus
minus,
EA sin theta and plus EB sin theta will get cancelled.
yeah, absolutely correct. Now it is a simple one. So EA sin theta, EA sin theta, this will cancel. And we will have minus 2EA cos theta I hat, right? So what is the magnitude that we got? Magnitude is this one, right? Minus I hat is the direction. So this is telling us that the direction of the electric field would be in which direction? So this would be the direction of this color may be not visible. So we choose the more visible color. Yeah, so this would be the direction of the magnetic field, right? Minus I hat is this direction, right? Right, guys?
Yes, sir.
Okay, so magnitude from here, magnitude of EB we have got, this is 2EA cos theta, right? EA we know that is KQ by R square plus A square. And what about cos theta? So if I calculate cos theta from here, cos theta from here, what would be cos theta? This triangle, what would be cos theta?
Mm.
Yeah, so let me just write down the triangle
Sir,
here. So we,
your microphone's volume is like very low, sir.
my
Uh,
volume is lower. Am I? Let me
yes, sir, you're
write.
audible. It's just the volume is like things are a bit low. Like it got lower than before.
Why this is low? So am I audible now? Clearly, am I
Yes, sir, you
audible
are
now?
audible. You're audible, sir.
My volume is lower.
Yes, sir, just a bit low. Things that might be my headphones, I think.
Yeah. You just increase because I have increased it to 100%. So my volume
Okay,
is
sir.
yeah.
Okay, sir.
So yeah, I'm asking that. Oh, what happened? Again, not again. Yeah. So this is theta. This is a. This is r. This is r square plus a square. So from this triangle, what would be cos theta? Cos theta is based upon hypotenuse, right? So how much would be that? How much would be that, Arsalan and Mir? Yes, guys. How much would be that?
Oh, yes, sir. R by, no, sir, it's breadth, so A by R.
A by hypotenuse,
Oh,
hypotenuse.
yes, sir.
Hy-
A by root R square plus A
yeah.
square.
So I can write it in this. Right, this is cos theta.
Mm.
So we can plug this value in here. Right. So I will write the one down in here. So this is A by R square plus A square half. So this is R square plus A square 1. This is half. So if I solve this one, so this is 2, that was how much? KQ by, and this was A, and this is R square plus A square, 1 plus half, right? So this would be how much? KQA divided by R square plus A square, and this is 3 by 2, right, guys? Is that correct?
Yes, sir.
And we know that, what do we know? That this A distance is very small as compared to this distance. So this distance, the distance between the dipole is very small. So then again, we can neglect this one, right? So R is very greater than A. So we can neglect this one, and magnitude would be how much? 2KQA divided by R square 3 by 2, because R square plus A square would be similar to R square, right? A square neglected. So this 2 will cancel, and you will get 2KQA divided by R. And if we write it properly, so if we write it properly, then this would be K and 2AQ by RQ. How much is this thing? What is this thing? Can you guys remember? Do you guys remember? Can you guys recall? How much
Yes,
was
sir. Uh, K to 2AQ, right? Uh,
yeah.
wait, sir, let me try to remember.
Mir, you also tell me, right? Why are you silent? This we have when we were doing this
Sir,
axial point. Yes.
yes, sir, in which?
So distance into charge. Charge separation into distance. So what is this thing? That is dipole moment, right?
Yes, sir.
Separation into charge. So that is dipole. So this is Kp by Rq. This is the magnitude at equatorial point, right? And we already know the direction. So direction was minus I hat, which was opposite to this direction. This is P hat direction, so this is minus P hat. So we can write this one. If I write it in vectorial form, so this is Kp minus P hat divided by R. So this is minus Kp by R. this is the electric field at the equatorial point, right? Is this part clear?
Yes, sir.
So what did we do? Let me recap what did we do. So we had these two charges, right? We had this point which was the equatorial point. This separation was A, this was R, this was minus Q, this was plus Q. This was the direction of the dipole moment, right? Let me write it as P. And then we calculated the electric field due to minus charge. So this was in this direction, right? And then we calculated the electric field due to this one. So this was in this direction, right? Let me write it as EBEA. And then we saw that this was theta. This was theta. So EB has two components. One was this EB cos theta, and this was EB sin theta. Similarly, this one has had two components. One was this EA cos theta, and the other one was in the downward direction, EA sin theta. So which component will cancel out? Which component will cancel out, guys? From here, which component will cancel out? So sine theta component got cancelled and we had only this one, right?
It's sir, I have a doubt.
Yeah.
Yes, sir.
What
So
is?
EA and EB cos theta are in the same direction. So that's why they're not getting cancelled out, right?
Yeah. So EB sine theta is in the opposite direction. That is why they are cancelling out, right?
So what if it's not opposite in the sense that, it's like directly, with each other? What if it's parallel to each other?
Yeah. Yeah. So
Will it
you
get
saw
cancelled
that.
out then?
Yeah. In here, this one was okay. So these one were parallel. Cos theta
Okay,
ones
then.
were parallel. So they were adding, right?
Okay, fine. Okay,
So
sir.
this one will cancel. This one will add up. Sine theta will cancel. So that is what we saw in here. So sine theta 1 got cancelled, right? Because these had same magnitude. So sine theta got cancelled and cos theta component got added. This is what we saw in the vector decomposition, right? So that is what I am saying here. So sine theta 1 because EA was equal to EB. So sine theta 1 got cancelled and cos theta 1 got added up and you got 2EA cos theta. So this is, I'm writing it directly. And that is what we have solved. So we saw that the overall electric field was in this direction. This was E equatorial. And this was in the opposite direction as the dipole moment. In the case of the axial point, what did we see? In the case of the axial point, we saw that E net, E axial was in the same direction as this one, right? But for the case of the equatorial one, we got the opposite direction. So any questions, any doubt in this electric field due to dipole? Any doubt?
No, sir.
Okay, so please note it down. And I have written, yeah, I'm prepared, but you guys please. This is the main diagram, and yeah, please one of these. Yeah, whenever you guys want me to scroll down, please let me. Is this
Yes,
clear,
sir.
Mir? Is this clear, Mir? Yes, Mir. Okay, so if you have any doubt, Mir, you can always ask, right?
Yes, sir. Scroll down.
Is that okay?
Yes, sir. Yes, sir, just scroll a bit more down.
More down.
Mhm.
Yeah, so the idea was that we found out the electric field. Electric field due to A, due to B. Two contributions were there. So we found out those two, we resolved those two vectors, and then we found out the magnitude was same. So then we added them and we found the result.
Sir, I'll be going to the washroom for 3 4 minutes. I'll just come back quickly.
Yeah, yeah. So yeah, whenever you come back, please give me what a
Yes,
sign that you
sir.
have come in, right?
Yes, I'll just raise my hand when I come back.
Oh, okay. Yeah. And in the meanwhile, if you have any doubt, please add it because this topic is very important. Derivation of electric field due to dipole is very important. Yeah, so we have to wait for Arsalan to come here and then I will scroll down. So in the meanwhile, you can also ask me about the doubts, please, right? Please, Arsalan.
Yes, sir, I'm back.
Hmm. Okay, so did you note down this part?
Yes, sir, just 1 sec.
Oh
Just give
yeah,
me
yeah, no
20
worries.
seconds more.
Yes. Yeah, whenever you have noted or pronounced,
Yes, yes, scroll down.
done. Okay, so then you guys, and we can directly do this problem, but I have shown you guys to do it in a resolution of vector space. So I have also shown you guys how to just write the components and cancel each other out. So that part you can also put it down and then you can directly get this one. Otherwise, we can use this Victoria's array. You guys want to go down.
Yes, yes, scroll down.
This I have written that why this cos theta would be this, right? So you can write it in here in the right hand side to just show that why this would be this, or you can write it in the video. You guys have written this. Some guys noted.
Yes, sir.
Okay. Yeah. Yes, noted.
Yes, sir.
So please, yeah, this one I just told you guys to understand, right? Because we can directly get this result when we use this relation, right? So these parts I got because so in the first method I solved all these resolution, right? And then we got this relation finally. But we can also directly use, right? We can also directly use this one. And from here, this diagram, we can say that this part will cancel out and only the cost components will, right, they will contribute. So the contribution will only comes from the cost component. So we can just directly write this result and then we can write what is cos theta and then we can solve this. So this is direct method, right? So you guys can also write this one. And from here, you guys know the result, how to calculate. From here, you guys. So also note down this picture, right? Please note down this picture. And if you guys have any confusion, please tell.
Yes, sir.
Yes, whenever you guys have noted down, please tell.
Yes, sir.
Yeah. Okay, so now let us recall or recollect what we have done in this dipole, right? So what we have done in this dipole thing. So we had this dipole, right? We had this dipole with a separation 2a, right? And this was the direction of the dipole. So first we calculated the electric field at this point. We calculated the electric field at this point, which we called the axial point, right? And what was the direction of the electric field? So direction of the electric field was this direction, right? Same as the dipole, right? And then we calculated the electric field at the equatorial point. And let's say at this point we calculated. At this point we calculated. And what was the direction of the electric field? In the direction or against the direction of dipole? What was the direction? Yes, we just saw that this was the direction of the electric field, right? Right, guys?
Yes, sir.
So, and we saw that equatorial was against the direction of dipole moment, axial was in the direction of the dipole. And we saw that magnitude was for axial one, this was 2 kp by r cube, and for equatorial one, this was kp by r cube, right? So we saw that E axial was double of E equatorial. This is what we saw. And we also saw that electric field due to dipole for both the cases. This was varying like 1 over R. So these are the information that we can collect, right? So please note down this diagram. Please note down and write down all these.
Yes, sir.
Yes, whenever you guys have noted it down, please
Yes, sir.
done. Arsalan, you have
No,
noted
sir.
it down or no?
Just a bit more I have to.
Yeah, please note it down. And you guys will have this class assessment today. So after this class, please take that class assessment.
Yes, sir. Sir, should we note what you wrote above?
Yeah, this one is also important, right? What is the magnitude that we found?
Yes, sir. Okay, sir. Done.
Then, okay,
Yes,
so
sir.
now let us understand a very important topic, which is electric field. Okay, so what are electric field, right? So there are not actual lines; they are just a pictorial representation. And this one is a hypothetical concept, right? Hypothetical concept is that these are not physical things, right? These are not physical things. These are conceptual things, which helps us to understand what would be the direction, what would be the properties associated with the electric field, right? So electric field lines. This one is a hypothetical concept. It is a hypothetical concept, and this is a geometrical representation which helps us to, uh, to understand the the properties associated with associated with the electric field, right? So these are the things about electric field lines, and it has basically eight properties. So we have eight properties of electric field line, and we will understand them one by one. So how to remember these eight properties? So just remember these important terms. One is tangent, right? Second one is relative density. Third one is positive and negative polarity. Fourth one is continuous. Fifth one is longitudinal attraction. And sixth one is lateral. So longitudinal contraction. And then we have lateral pressure. Seventh one is the neutral points. And eighth one is conductor. Right. So these are the eight properties of the electric field lines, which we will discuss one by one. And this will help us to understand the nature of the electric field very easy. Right. So if we remember these things, then we can write all the eight properties. These are the basic eight properties of the electric field line. So let us understand them one by one. Right. So first property is that tangent tangents uh, on an electric field line gives the direction of electric field. That is why the electric field lines never intersect each other because we will have two tangents from that point which will give two directions of electric field which is not possible. So all these things from the pictorial diagram we can directly understand, right? So this is that, let's say this is the direction of the electric field line. And if I draw a tangent at this point, so tangent at this point, let's say this is the field line is going like this. So tangent at this point would be this, right? tangent at this point would be this. Right. So tangents at the electric field lines will give you the direction of the electric. Right. So if I draw a tangent on the point on the electric field line, so that will give you the direction of the electric field. So at this point, electric field is in this direction. At this point, electric field is in this direction. At this point, electric field is in this direction. Right. So this is what I call the tangents on an electric field line will give the direction of the electric. And let's say the two electric field lines are intersecting. Let's say this one and this one. Right. So at the intersecting point, when I draw the tangent for this one, so this would be this, right? This is electric field. And at this point on this line, the electric field would be this one. So at this point, there are two electric field directions, which is not possible, right? That is why we cannot have two electric field lines intersecting each other. Is this point clear, guys? So one is that if we draw the tangents on electric field lines, that will give you the direction of the electric field. So this is one property we can understand with the use of this electric field line. If we have electric field lines given and we draw the tangents on that electric field line, so that will give you the direction of the electric. Is this point clear, guys?
Yes, sir.
Okay. And the second point was so second point was relative density, right? So the relative density of the electric field lines give the strength of the electric field. So therefore, more denser the electric field line, more is the strength of the electric. Similarly, lesser density means that lesser strength of the electric. And similarly, if I write this, similarly, lesser denser means less strength of the electric field, right? So how can I represent that pictorially? So let's say that you have this. So you have some charge, right? And so you have some charge at this place, and these are the electric field lines. So if I'm calculating the electric field at this point, and if I'm calculating the electric field at this point, right? In this region I'm calculating, and in this region I'm calculating. So how many electric field lines are there in this region? This is relatively denser, right? So there are one, two, three, four. Four electric field lines in there, and we have only one electric field line in there. So
Yes, sir.
which electric field would be higher and which electric field would be less strength-wise?
So EA will be higher
Yeah. So
strength-wise, and
EA
EB will
would
be lower.
yeah. So this is what we call the relative density. So if we have a large relative density of the electric field lines, then that part will have more strength of electric field, and comparatively the lesser one will have less. This is called the relative density. The third property is the polarity, right? So the positive charge will have uh, will have the electric field line which would be outwards or outgoing, and for a negative charge particle, all the electric field lines would be incoming. So that we have seen from the properties of the Coulomb's law, right? Negative charge is attractive, positive charge is
Mm.
repulsive, right? So due to positive charge, all the electric field lines will go outward, right? And due to negative charge, all the electric field lines will be income. Is that clear, guys?
Yes, sir.
So that is why when we see these problems, right? So now you guys can understand that if we have a negative charge, then electric field would be incoming, right? If we have positive charge, electric field would be out. So from electric field lines, this is more understandable, right? Clear?
Yes, sir.
Yeah. So this one was about the polarity, and the fourth property is very easy to understand, and that is quantity. So electric field lines are continuous in nature, right? So let's say we have this positive charge, and electric field lines are going in this way. So they will not break here and then they will go from here. So they will not. Let's say this is positive. So this will not happen like this one, and then from here it is there. This will not happen like that. It will be continuous, right? So this is the fourth property, and yeah. So I will write the fifth and sixth one also. So fifth one is about longitudinal contraction. So longitudinal contraction of the electric field line spells out the attractive behavior of the charges or electric fields or electric fields, right? So let's say we have this negative point. We have this negative point, and all the charges are coming at this. So all the charges are all the charges are contracting at this point, right? They are contracting. So they are coming at this point. So this tells us about that electric field are attractive in nature. Charges are attractive in nature. Okay. Similarly, we have this lateral pressure, lateral pressure of the electric field line talks about the repulsive behavior of the charges. Right. So let's say we have positive charges, right? And from this one, the electric field lines are going like this. And let's say we have another positive charge. So this from this one, electric field lines are coming like this. So they will not intersect, right? They will not converge, but they will provide a repulsive force, right? And this one is called the lateral pressure. So this is showing that they are repelling each other. Repulsive nature they are showing, right? So this is lateral pressure, and the seventh point is that the electric field line never intersect the neutral points, right? So they go parallelly the neutral point and meet at infinity. What do I mean by that? So we have these positive charges, right? And what is the neutral point? What is the neutral point? Can you guys tell me? What is the neutral point? Arsalan and me. Neutral point we have when we were doing the symmetry of the charges. So then we did this neutral point. What is the neutral point, guys?
So the neutral point is so
Neutral point is a point at which the electric field is zero. E net electric field is zero. So we have calculated that we have two positive charge, and at center of this geometrical center of these 2 point charges will have a neutral point, right? You guys remember
yes,
that
sir.
now? Yeah. So at neutral point, the electric field lines will never intersect. So they will go like, right? So they will go
Yes, sir.
parallelly and they will meet like from here they will go like. So this is due to this neutral point, right? They will try to meet it in the infinity. Is this point clear?
Yes, sir.
Okay, so the last property is the conductor property, right? So electric field lines falls perpendicularly to the conducting material. So they fall perpendicularly, right? So let's say we have this conducting sheet, right? We have this conducting sheet and we have this charge which is kept at here. So this is a conductor, right? So if let's say this is a positive charge and electric field lines are emanating from this one, emanating, so they will fall perpendicular, right? They will fall perpendicularly to this conductor. And let's say if you have a spherical conductor like this, so on this spherical conductor, they will fall perpendicular, right? So that is the property of the conductor. That electric field lines fall perpendicularly to the conductor. Is that clear, guys?
Uh, yes, sir.
Yeah. So these are the basic eight properties of the electric field line. So if we do it in a pictorial manner, so for a single charge, it's a positive charge. What is the electric field lines? So they are coming out of this positive one. Okay. And for the negative charge, we have this negative charge. So electric field lines are falling on this negative charge. So that would be income. And let's say we have two charges, positive and negative one. So from this one, the charges will come out and this will fall perpendicularly, right? So you guys can see that in negative charges, all the electric field lines are coming inwards. And for
Yes,
the
sir.
positive charges, all the electric field lines are going out, right?
Hmm. Yes, sir.
Yeah. So this is due to the positive and negative charge. And the fourth one is, let's say, between positive or negative and negative, we can also. So positive one. Let's say we have this positive charge and we have this positive charge. This will have a neutral point in here. So this will go down. My drawing is bad, but this will be something, right? Right. This is due to the positive and positive. And let's say if we have a conductor, let's say we have this conducting plate. So if this is the positive charge, so it will fall perpendicular. Right. On this surface, they are falling perpendicular. These are the properties that we have understood. So any doubt in the following properties that you guys have? Any doubt?
No,
Yes?
sir.
Okay, so please note down these. These are and these electric field lines, they may come in just 3 or 5 months.
So I already noted this part. Can you scroll down?
Oh, you guys have already noted this. Meera, have you noted down this part?
हाँ सर जैसे में
Oh, then please. So after a long time, we have heard you guys. What is happening? Yeah, whenever you have, Meera, if you have any doubt, please ask. Right? We are all here to understand. And if you have any doubt, please don't keep it to yourself. Yeah, whenever you guys want me to scroll down, please. Yes, done me. Okay.
यस सर स्क्रॉल डाउन
Then please go down. Whenever you guys have noted it down.
Yes, scroll down. Yes, I noted this part already. I
Just
think so.
one
This like
only.
last. Yes, I noted some of the stuff in between. That's why. Yes, I didn't note this time. Wait for this.
Yeah, me, if you have also noted it down, please you also noted it.
Yes, sir. Scroll down.
Done. What
Yeah.
about you, Arslan? Done.
Yes, sir, done. Just scroll a bit up. You just need to draw the diagram. Yes, sir, done. Yes, sir, scroll down. Yes, sir, a bit more down.
Bit more down.
No, sir, this is done. This I'm good. Yes, sir, I'm done.
Done. What about you, Mir? Not yet.
Just a minute, sir.
Ah, okay, so what are the topics which are remaining in electric charges and field? One is force on charge particle in an external electric field. And then you have torque, and then you have electric flux. So three topics are right. Electric flux we will understand about because topics are remaining. So in the next class we'll try to finish that up. Then this chapter will be over, then we'll start with the second. Done, Amir.
Yes, sir.
Done, everyone.
Yes, sir.
Okay, then please,
Sir, just a minute.
oh, one.
Yes, sir. Scroll down.
This is conducting sphere. Let's say this is a negative charge one, and this is conducting field. So we'll talk about these in when we'll do the electric flux. Done, right?
Yes, sir. Scroll down.
Yes, right.
Yes, sir. Scroll down.
Third and fourth diagram.
Yes, sir. Scroll down. Almost done. Save it. Yes, sir. Yes, sir. I'm done.
Yeah. What about you, Meet? Noted.
Sir, I'll be.
The second one.
I have to go somewhere. So I'll just write the exam quickly.
Yeah. You take that class assessment. So yeah, you can leave Allah Hafiz Arsalan and please take that class.
Allah
Sir,
Hafiz, sir.
Yes, me. Yes.
second one.
Second one. Yeah. This one. Is that okay, Meet?
Yeah, sir. Done.
Yes, noted. Meet.
Yeah, sir. Done.
Okay, this part also noted. Fifth one.
No, sir. Just saying.
Yes, whenever you have noted it down, please.
Done, sir.
Yeah. Okay, so yeah, the next class we'll talk about the other topic and